Let's use the example of sweating as an application of why this compartmentalisation of body fluids are so crucial. So in sweating, you've got the surface of the skin and you've got a sweat gland. And the sweat gland is basically a coiled tube in the lower parts of the dermis. And of course you're sweating water, and that is derived from the plasma. So around about a sweat gland, you're going to have an array of capillaries. There'll be an arteriole taking blood to the area. There'll be a venule draining blood from the area. And what the sweat gland will do is it will extract water and some salt from the plasma, put it into sweat. That will go up the sweat gland duct onto the surface of the body, where it will evaporate and the latent heat of vaporization will be extracted from the surface of the body. But what we're noticing here is that water and salts goes from the blood, from the intravascular compartment into the sweat gland duct, and is ultimately lost from the surface of the body. So what this means in terms of this diagram is that water molecules are lost from the intravascular compartment. That means as sweating goes on, there's going to be less water in the intravascular compartment. Less water. But we do not sweat plasma protein molecules. The plasma protein molecules don't go from the intravascular compartment into the sweat gland. No, the plasma protein molecules stay here, where they were to begin with, in the plasma. So this means that now we have relatively more plasma protein molecules compared to the amount of water molecules. Because if you consider the total amount of plasma protein molecules in the intravascular compartment, after water's been lost through sweating, that total amount of plasma protein is going to be the same, but there's less water. That means the plasma proteins are going to be more concentrated, and that's going to increase the osmotic potential of the plasma. So when water's lost from the plasma, if all the other constituents, or certainly if the proteins stay the same, then that's going to increase the osmotic pressure of the plasma. Now, as we know, tissue fluid is formed at the arterial end of the capillary and is reabsorbed at the venous end of the capillary as a result of osmotic pressure. But now, after sweating, the amount of osmotic pressure is increased. The blood is now more osmotic. So if the blood is more osmotic, does that mean we're going to get more or less reabsorption of tissue fluids? Well, if the blood's more osmotic, I think you can see that that means we're going to get more reabsorption of tissue fluid. So what will happen is more fluid will be absorbed, particularly from the venous end of the capillary. So we'll get fluid moving from the interstitial compartment into the intravascular compartment. And that will restore the volume of the intravascular compartment. And this is absolutely essential, because if we don't restore the volume in the intravascular compartment, that will lead on to hypovolemic shock. The blood volume will drop. So you might lose a litre or two in sweat. You might even lose 3 litres in sweat. And if that water wasn't replaced, then you would be hypovolemic and you would be completely incapable of taking any further action. You would die if you lost 3 litres of intravascular circulating fluid, in fact. But fortunately, as well as the 3 litres of water in the intravascular compartment, we've got 11 litres of water spare in the interstitial compartment. We noted there's 11 litres of water here. So as well as 3 litres of water in the blood, you're kind of carrying a spare 11 litres, as it were, in the interstitial compartment. Because it doesn't matter too much if this compartment dries off, but, well, not dries off, but becomes, if the volumes of water here are reduced. But if the volumes of water in the intravascular compartment are reduced, that's hypovolemia. That means we can't take effective action. Now, if you can drink all the time, of course, it's not such a problem. But human beings are designed to survive. So if you're in a hot day, if you're sweating, if you lose 1, 2, 3, 4, 5 litres of sweat, you're not going to become hypovolemic because you've got this spare water in the interstitial compartment. You might feel thirsty, you might not feel brilliant, but you're going to maintain your blood pressure. That means you can keep walking until you come to an oasis, or in modern terms, if you come to a tap, you can rehydrate. So you've got this spare water here to go in, maintaining intravascular volume. Now, over time, it's fair to say that the amount of water here will be reduced. And if the amount of water here is reduced, then solutes which are present in the tissue fluid will themselves become more concentrated. That's going to increase the osmolarity of the tissue fluid. But fortunately, look what we've got here. 28 litres of spare water. It's not really spare water, but there is 28 litres of water available inside the cells in the intracellular compartment. And of course, it's not one intracellular compartment, it's trillions of individual intracellular compartments. So if someone loses a lot of water, water's going to move from there to there, that's going to become more concentrated, and then water will move from the intracellular compartment to maintain the volume of the interstitial compartment. And of course, if we maintain the volume of water in the interstitial compartment, that means we can maintain the volume of the intravascular compartment, thereby preventing hypovolemic shock, maintaining blood pressure, allowing us to keep going, keep functioning, until we can find a source of water. So this is all predicated on the fluid compartments. So again, we see the vital importance of the intravascular compartment, the interstitial compartment, and the intracellular compartments.